Hi, I'm Millie from Izon Science. In today's video, we'll be covering some of the most recently discovered nanoparticles in the extracellular landscape, exomeres and supermeres. Intercellular signalling as we know it only seems to get more and more complex. Recent years have seen EVs dominate the space, but exomeres are gaining popularity in the literature. And while exomeres are often included under the umbrella of EVs, and are often included in EV conferences and the likes, technically, they are not EVs, as they are non-vesicular. In keeping with the recent MySev 2023 recommendations, they actually are categorised as extracellular particles, and not extracellular vesicles. Exomeres also differ from EVs by being predominantly protein-based, from what we can tell, and much smaller than even EVs, up to a staggering 80 times smaller. And while exomeres may play a role in intercellular communication, their biogenesis, composition, and function is unclear. What is known so far is that there are a variety of proteins in exomeres, including ribosomal and scaffolding-related proteins. And to complicate matters further, it's not just exomeres making a splash in the world of extracellular fluid. Supermeres are even smaller, around half the size of exomeres. Their name comes from the logic that they exist in the supernatant of exomeres. That is, once all exomeres and anything larger have been removed from a solution, the supermeres are the next largest constituent. Supermeres, like exomeres, are non-vesicular and at this stage also come under the extracellular particle family. Well, at least for now. See, supermeres are so small it's unclear whether they are a particle or a protein aggregate. We do know that supermeres are morphologically different to exomeres, and it appears that most extracellular RNA is associated with supermeres rather than small EVs or exomeres. It's reported that supermeres can be internalized into cells through micropenocytosis, just like small EVs. This internalization appears to be present in a wide range of organs, such as the heart, liver, and they've even been shown to cross the blood-brain barrier. Evidence suggests that supermeres could be an important candidate for biomarkers or for developing therapeutic targets, especially in diseases where their cargo appears to play a functional role, such as in various cancers, cardiovascular disease, and even Alzheimer's disease. While research around these tiny extracellular particles is intriguing, the size of exomeres and supermeres make them very difficult to study. Isolating these particles has, until now, been particularly problematic and impractical. Here at Izon, we have released our QEV columns in the 20 nanometer series, allowing isolation of extracellular vesicles and particles down to 20 nanometers in diameter. Best of all, it's a quick and gentle method that is bound to help speed up your research in this area. If you are using ultracentrifugation for EV isolation, it does pay to keep these particles in mind. With extreme G-forces, you may be more likely to isolate a high proportion of these small extracellular particles as contaminants, while also causing EV aggregation, both being unwanted outcomes for EV isolation. Currently, only transmission electron microscopy and atomic force microscopy can accurately measure exomeres and supermeres on a particle-by-particle basis. Yet both require significant processing time and offer low throughput, making them less than ideal options. And while exomeres and supermeres are likely very important to the intercellular signalling picture, EVs remain in the limelight for now. So if isolating EVs is your priority, be sure to consider these potential contaminants or aggregates in your study approach. If your goal is to avoid them, or isolate more of them, check out our website for the full QEV column range.